Bismillahirrahmanirrahim. Assalamu alaikum and welcome. Today we're going to dive into a topic from the grade 12 chemistry textbook that's not just in the book, it's happening inside of you right now. We're talking about chemical equilibria. You know, it's this constant, invisible balancing act that, and I mean this literally, keeps you alive. And to get our heads around it, let's start with a simple question you might have even wondered about yourself.
Seriously, think about it. You grab a can of soda, which is pretty acidic, right? You drink it, but nothing dramatic happens. Your body doesn't just, shut down. Your blood's pH, that's the measure of how acidic or basic it is, it stays incredibly stable. How is that possible? Well, that is the mystery we're going to solve today, and the answer is all tangled up in this amazing world of equilibrium.
All right, so to crack this mystery, we're going to need the right tools. We first have to understand how chemists actually measure how strong an acid or a base is. Believe me, this is the foundation for everything we're about to uncover.
Okay, tool number one, and it's a big one, the acid dissociation constant, or just K. So what is it? Put simply, it's a number. A number that tells us how good an acid is at giving away its protons when you put it in water. You can think of it as the official scorecard for an acid's strength.
And the rule here is refreshingly simple. A bigger Ka value means the acid is more willing to break apart and do its thing. So, the main takeaway, the thing to remember, is this. The greater the Ka, the stronger the acid. Easy as that.
And just look at the difference here. It's absolutely massive. On one hand, you've got perchloric acid, a super strong acid, with a Ka in the billions. Then compare that to acetic acid, the stuff that makes vinegar sour. Its Ka is a tiny, tiny fraction of 1. This just shows you the huge spectrum between what we call strong and weak acids.
Now, because those Ka numbers can get a little wild and awkward to write down, chemists have a little trick. They often use something called pK instead. All you need to remember is that it's the total opposite of Ka. So a high Ka means a strong acid. But for pK, a low number means a strong acid. Kind of like a golf score. The lower, the better.
Okay, so we've got our tools, we understand Ka and pKa. Now we can finally meet the real hero of our story and solve that soda mystery. Let's talk about these amazing chemical systems called buffers. They're basically the guardians of pH.
So what exactly is a buffer? Well, it's this special kind of solution that works like a chemical shock absorber. If you add a little bit of acid or a little bit of a base, the buffer's job is to just soak it right up and keep the overall pH almost exactly the same. It's incredible.
And this stability isn't just for fun. It is a matter of life and death. The numbers you see on the screen, that's the pH range your blood has to stay in. If it goes much higher or lower, it can be fatal. That is an unbelievably narrow window that our body has to maintain 24/7.
So how in the world does our blood pull this off? Well, the secret is the bicarbonate buffer system. Remember that soda? When you drink it, you're introducing a bunch of extra acid, or H+ ions. But check out this equation. Your blood is already full of bicarbonate ions, and they see that extra acid and immediately jump into action, reacting with it and turning it into harmless carbonic acid. Just like that, the threat is neutralized.
And what's so cool is that it works both ways. If your blood ever gets too basic, the other part of the buffer team, carbonic acid, swings into action. It donates a proton, neutralizes that excess base, and turns it into plain old water. It's this perfect, dynamic duo that keeps your blood pH right in that sweet spot. And there you have it. Mystery solved.
But this whole idea of equilibrium, it's not just some cool trick our blood does. It's a fundamental principle that shows up all over the place. In manufacturing, in medicine, in our environment. It's truly everywhere. So let's look at another type of equilibrium constant, the solubility product, or KSP. This one answers a really basic but important question. How much of something can you dissolve in, say water, before it just stops dissolving and starts piling up at the bottom? This is super important for things like purifying water or even predicting when solids will form in a chemical reaction.
Let's take silver chloride, for example. Its KSP value is tiny. I mean, look at that number, it's incredibly small. That number is basically screaming at you, I do not like dissolving. And chemists can use this constant to calculate the exact tiny amount of silver and chloride ions that can exist in the water at one time.
Now here's where things get really cool. We can actually mess with this equilibrium. There's something called the common ion effect.
It says that if you have something that doesn't dissolve well, like our silver chloride, and then you add another chemical that also has chloride ions in it, you actually make the silver chloride even less soluble. You're basically pushing the equilibrium backward, forcing more solid to crash out of the solution.
And this principle of controlling where things go isn't just for solids and water. It works for liquids too, and that's where the partition coefficient, or KPC, comes in. It tells you how a substance decides to split itself between two liquids that don't mix, like oil and water. Why does that matter? Well, think about medicine. Our body has watery parts, like blood, and oily, fatty parts, like our cell membranes. KPC helps drug designers predict where a medicine will prefer to go, which is absolutely crucial for making sure it works.
So from keeping your blood perfectly balanced to designing a life-saving drug, chemical equilibrium is this powerful silent force that's always at work. It's a constant push and pull, a dynamic dance of molecules. So the question I want to leave you with is this: what other invisible balancing acts are happening all around you, right at this very moment?